Well, welcome to the first recitation for 740. I assume you've been watching the lecture, so I'm not going to say welcome to the first lecture. This is a unique experience for me too, so this is the first time we're going to do lectures fully online and everything else, both online and offline at the same time. How are people finding the lecture so far? I'll start with that. Are they good online? Because I really want your feedback on this. This is the first time we're doing this. It's an innovative thing, and we'll improve over time. I think that's the hope. But your feedback is critically important because you're the people who are receiving this. And if you have any trouble, if you have any suggestions on anything, we'll try to accommodate as best as possible. So the lectures are understandable so far. Everything is good.
The board is really hard to read.
Yes, that's great feedback, and I realized that too. Initially, I was recording in SD mode, so some of the initial lectures are going to be hard to read. I apologize for that. As we go forward, I think for example, you will see in module 2, it'll be easier to read, hopefully. And going forward, it'll be even easier to read. That's the hope. But please give us feedback on how things become. So there are several things I would suggest in terms of making the board more visible for you. Have a larger screen. That helps. I know that's not necessarily possible, but I can see it better when I have the larger screen. The second is you can zoom in, I think, with some of the videos. Oh, good. We have people who are coming in late. Was it hard to find this room? Yes. Okay. Yeah. That's what I gathered. Did you walk into the Apple office? Yeah. Yeah. So you can zoom into parts of the video where the board is there, and I think the last thing is sometimes this is an issue with Panopta that we're using. Sometimes if the internet bandwidth is not high, basically it'll throttle what you see. It'll change the quality of the video, adapt the compression rate. And I've had terrible viewing experiences even with the HD videos from my apartment because my apartment's internet is terrible. And I know the reason because my router actually has been used for 8 years, I think. I've had my wireless router for 8 years and it's just not working anymore. So this is, I think, this is one good goal. You guys are being computer architects, designing computer architecture, so it's good to design architectures for durability. Design architectures that can last for hundreds of years. So actually, that's I'll derail a little bit since it's a recitation session. But one of the things that we will cover in this lecture is some of these emerging memory technologies, and some of these emerging memory technologies are non-volatile. So today, if you look at DRAM, dynamic random access memory, it's volatile, right? Basically, you need to refresh it to keep the data. But there are some emerging memory technologies that are non-volatile. Flash memory is one example of this, right? It can keep data for, basically, it doesn't lose data if you power it off. It can keep data for a long time. But if you want to have really durable memory, right now we're generating data at rates that we cannot imagine storing them for maybe hundreds of years, perhaps. But one thing I will just jog your memory on, jog your brain on is, can you design memory systems that can retain data for longer than hundreds of years? This is something we have not thought of that much, I think. So if you think of, maybe we'll have a lecture on this at some point, but if you think of how people store data from the very beginning of time, one of the most durable storage is carving stuff on the rocks, right? And you can see that stuff carved on the rocks even today. It has lasted for thousands of years. Now, when you think of some of these non-volatile memory technologies that we have, flash, for example, today, is it really durable at that level? I doubt that, right? That's you lose data even in your hard disks, and well, hard disks are actually very unreliable technology. But think about how to actually design systems that can retain data for hundreds of years, maybe in tens of years, right? So DRAM cannot even retain data for more than 64 milliseconds. But we'll challenge that also. We'll challenge that assumption. So you need to refresh every DRAM cell every 64 milliseconds today. That's a very short span of time. Some other memory technologies, like phase change memory, can retain data much longer than that. And we'll talk about that technology too. Flash memory presumably can retain data for much longer. But there are some issues with these memory technologies also. For example, when you write to a cell in flash memory, you can do that write only how many times? Do you know? Say? How many? I cannot hear. But for a multi-level cell flash, which means that multi-level cell means a cell stores multiple bits at a time. You can write only 3,000 or so times. And actually 1,000 is, as you scale the size of the cell, this number reduces because it's easy to lose the charge that you put into the floating gate in flash. So 1,000 times, you cannot even rewrite the cell many times. So that's another problem with these emerging technologies. So I think when you think about designing durable systems, one of the big components of a durable system is main memory and storage. How to design that reliably becomes very, very interesting. And if you're interested in thinking about some project topics, this is a very good area to do a project on, especially if you're interested in doing research today, how to design much more reliable memories that can store data for a long amount of time. Okay? I just wanted to give that. We'll derail a lot, I think, in these recitations. So I guess let me go over the basics very little. I'm not going to, this won't be a deja vu. I'm not going to try to duplicate what we've done in the online lectures. I guess first question, how many people have watched Module 0? I hope everybody here. Everybody? Okay, great. So everybody is familiar with modules. How many people have watched modules 1.1 through 1.3? So, maybe. 1.1? Almost everyone. 1.2? Okay, almost everyone. So that's 1.1 and 1.2 are due this week. So I'd encourage you to watch it. And what I'll assume, I guess let me go over through the logistics very quickly. I'll introduce some people over here also. But since you watched this, I'll go through this. You haven't met Seth probably, but Seth is a co-instructor in this course. And he's mainly catering towards us computer science students. But you can certainly attend his office hours and lectures as well. It'll be a different view that is provided by him. But it should be fun, hopefully. But you don't have to. You can attend only one set of lectures. I know it can be overwhelming if you actually go to many things. OK. And my TAs, not all of them can make it today. But on Friday, we'll have the full set, I think. Hongi is here. So if you have any questions, you can certainly contact them. And I believe online students are seeing everything over here, too. So actually, we have several students online. We can, I guess, 7 of them. Hello, guys and girls. OK. I guess they can hear me, but we cannot hear them, right? OK.
If they'd like to speak, you can allow them to speak, but it doesn't look like anyone wants to.
OK, yeah. So I guess whenever you would really like to speak, you can raise your hand, and somebody will prompt me. So I guess if you attend this online at some point in time, you can know how to use it, too. OK. So there are 2 other very bright TAs who have taken this course before, Tyler and Brian. And they're not here today because they have conflicts. But I think Tyler may be attending online. I'm not sure. But you'll get to meet them also. And we'll all have office hours that are... So this to be determined is gone. We have only 3 TAs for this course. So they'll have... please use their time wisely. But they're very bright. They've been doing research on computer architecture for a while. And they've taken, I think, 447, 740, and 742 from me. So they know what the course structure is. Actually, Hongi hasn't taken 447, but he knows it well. He's been to Michigan. OK, you all know the website, I assume? OK, so I'm not going to go through this. But everything will be on the website as well as the Akatar site. So I'd like you to use the Akatar site to get to the lectures. So I guess one question I'd like to get a poll. Who, and the online people can respond also. Please respond through by typing. How do you find the Panopto videos? Are they easy to use? Okay. How many people watch the Panopto videos? Let's see a show of hands. Okay, most of you. How many people watch the YouTube? Okay. Is there a preference do you have? Yes?
Silverlight does not install on my browser.
Okay, which browser do you have? Firefox. So excellent, I have the same problem actually. It's not only me then. That's good. Yeah, it didn't install on my browser also. And you have a Mac? Or Linux? Yeah, I use Safari. It works on Safari for me. But for Linux, I think maybe Hongi can help with that.
Linux, you cannot have the nice layout as Mac or Windows user have, but then you can still watch the video. You just click on the play button, it will play.
Yeah, that works.
Oh, that works? Okay.
But then the layout will be not as.
Oh, the podcast works, you're saying.
Yeah.
I see, but not the.
Yeah.
Yeah, but we would like him to be able to watch the entire thing, right? Because that's a better.
Suggest you either install Wine or a virtual machine. Moonlight
Okay.
doesn't work.
Okay, I see. Yeah, this is a problem with Silverlight. We'll need to get Microsoft to do the right thing at some point in time, but that's probably not going to happen. Okay. Okay, Blackboard, you're not going to need to use it that much, hopefully. We'll do most of our communication through Akatar, EC learning environment, as well as the website. Okay, so whenever you need to email us, please email us at the 740 official email address. You know all of this, so I'm going to skip this. But let me talk a little bit about recitations, because this is...
If I can interject real quick before.
Oh, sure.
So, my name is Joseph
Yep.
Friedman, and I work with Agatar. I'm the course manager for this website, and so anything that the TAs and owner wants done, I work to complete to make sure that he has the best experience with his content, and so that you guys have the best experience with taking this course. And so your feedback is crucial because you are the first set of students to go through this online iteration of this course. So any problems that you guys might have, anything that comes up, good or bad, we'd love to hear it under the Agatar environment in cmuece.agatar.com. There's a little help feature in the top right corner, and you can submit a ticket. There are tickets to submit just as feedback and suggestions, and I encourage you to use those. Or you feel free to email owner who can, or his TAs who can forward the feedback to us.
Yeah. Yeah, you can certainly email 740official@ec.cmu anytime, and we'll try to make this the best experience that you can have. So it'll be better than a hopefully just fully in-person course. That's the idea, so that you can study the material beforehand and ask. We can go much more in deep to the material here in the recitation sessions, which is hopefully what you all want to do, right? It's an advanced graduate course. Okay, so that's yeah. And Joseph, you can, if you have any technical issues, Joseph will be here to help us at any time, especially for the online students too, right? Remote students. Okay, so the purpose of the recitation is to actually enhance what we've learned in the lectures, online lectures. So I'd really like to encourage you to come up with questions, because sometimes I'll just come here and sit and ask, do you guys have any questions? What do you want to talk about today? Is that fair? Okay, we can talk about, for example, more advanced topics than what's covered in lectures, research that's going on in the field. We can go back into some of the fundamentals and history of how things have evolved. These are normally things we cannot do in a regular course where everything is, where we don't have the online recordings. So I'd like to definitely go deeper into project topics, for example, during these recitations. We can potentially talk about some topics today, and I've already given you one example today of using emerging non-volatile memory technologies and enabling them somehow. And there will be a project handout related to this. Okay. One thing in terms of scheduling, we'll try to dynamically adjust the frequency of the recitation sessions depending on demand and what we cover. Who wants to attend 6 hours per week recitations? No one. What about 2 hours per week? Is that better? So I think 2 hours is probably a sweet spot. But we can expand depending on the demand. For example, when closer to when the project proposal is due, we can make it 3 hours, 4 hours potentially, and we can have some online sessions. So that's the beauty of an online course, in my opinion, or a hybrid course. We can do this dynamically. Any questions or any suggestions on that? I'm open to your feedback because you will be a very active participant of this course. And this is a graduate course. It's not an undergraduate course anymore. You're supposed to know some of the basics. So you've done the background material, hopefully, right? How many people have studied some of the background material that we put up? Oh, excellent. Excellent. So if you've taken 447 last semester with me, you're already up to date. But if you haven't taken it, please study it. Okay. Office hours, I think you can come to office hours also. Okay. Let me see if I have anything else to cover here. I don't want to cover this. Yeah, so I think here, let's go over this. Certainly learn the material and research it. Because this is a research-oriented course, right? You will do a research project. When I say research project, it could actually be an implementation project also that involves something important in computer architecture. For example, if you want to design architectural mechanisms to accelerate a particular application that's very important, a data-intensive application. For example, genome sequence and alignment. That could be an interesting project. If you're interested in something like that, I would suggest talking with Hongi, because that's his research area at this point. He's designing techniques to accelerate these genome sequence alignment algorithms. And we can talk about that later on if you're interested. But certainly researching the material would be good. I'll give you a lot of readings over time, but you will learn the best if you do the readings beforehand as much as possible. And there will be required readings for each lecture. I would definitely do those required readings, but the remaining readings, whatever you can do over there, that will enhance your background and give you ideas for projects as well. Especially in the first couple of weeks when you're forming your project proposal, I would suggest you read a lot. I think continue going forward, read a lot anyway, right? It's fun. I wish I had more time to read these days. Okay, these are obvious things, yeah. Yeah, some readings you'll need to write reviews for, and how many of you have done the reviews? All right. Okay, that's a good number. One of them, maybe two. Okay. I know you have 3 reviews, which we'll try to throttle a bit. We'll try to distribute over time. One of them is an overview paper that I wrote on memory scaling, and there are actually a lot of research ideas in there. If you're looking for research topics, that memory scaling paper is a very good paper that looks at directions. I'm not saying it's because I wrote it, but but that does look at a lot of different directions. So I'd be happy to talk to you about any of those topics. I think emerging memory technology is one of the topics over there, one of the solution directions that I mentioned. The second review paper is written by Yale Pat, and that's on requirements, bottlenecks, and good fortune, right? The agents of microprocessor evolution. And that's actually a paper that was written at the cusp of this decade, like actually I guess the previous decade now, in 2001. And that looks at some of the challenges in designing a microprocessor. And its main outlook is actually designing better single core processors. So you can see a different viewpoint in that. So that looks at the processing aspect of potential challenges that you have in the processing side. And the memory scaling paper looks at the challenges you have in the memory side. So I wanted to give these to you so that you have both sides. And one is, of course, written 12 years ago. So that's, it's good to critique that paper with that in mind. Because every paper that you will read will be different at a different point in time, right? For example, Amdahl's paper that you should definitely read is written in 1965, right? And that's a long time ago. Even the terminology is a little bit different. How many of you have read the Amdahl paper? Oh, excellent. How many of you haven't read it? Okay, now you have to read it. Good. It's good to be honest. But that's a very short paper, and definitely read that. Yeah, I guess I have this in the lecture too, but when I ask this question, I talk about Amdahl's law a lot when I visit places. And when I ask the question, who's read it, it's usually the professors in the room who read the papers. I guess when they haven't read it, they may still raise their hand, I guess. But it's good to read it and raise your hand after you read it. Okay, so this is something I cannot emphasize more. Start the project early and focus on it. This is a very project-oriented course. Yes, Jesse?
I read Amdahl's paper and then also the refutation of it that was published in 1988 that proposed an alternative model.
Yeah, that's Gustafsson's paper.
I wanted to know what your opinion of competing models was. Because one of them is that the problem size stays constant, and therefore you have an upper bound on the improvement in performance that you can get. And the other one says that given an arbitrary problem, you see this much reduction in performance when you bring it back to 1.4. So which do you think is more relevant today?
Yeah. So that's a great question. I think maybe I'll try to bring up that paper also. This is John Gustafsson's paper, right?
Would you mind repeating the question for that?
Yeah. So the question is, after Amdahl, let's see if I can, Gustafsson's law. Do you remember what the name of the paper was?
Rethinking Amdahl's law, I think?
Yeah.
That might have been the more recent one.
Revalidating Amdahl's law. There you go. Okay. This is a more recent one, I think. I think there's another paper that.
I think it's that one.
Yeah, I think there is one that was actually. Oh, this is the older one or newer one?
That's the older one, but it looks like it's been reformatted.
Yeah, it's been reformatted. Okay, so the question is, Amdahl's law makes some assumptions, right? And one of the assumptions is the problem stays the same, right? As you scale the size of a number of cores, right? That's the assumption. So people have actually written a lot of papers trying to refute Amdahl's law, and they've come up with different theories. And this is one of them. This is one of the more famous ones, actually. And I don't believe, I'm not sure if this actually introduced the terminology, but this paper assumes that problem size also scales as you increase the number of cores, right? Is that correct, Jesse? So if you have problem sizes scaling as you increase the number of cores, Amdahl's law doesn't necessarily hold, right? This is called the strong scaling. I'm not sure if you read this more recently, so maybe you can help me out in terms of the terminology. But I believe what they say is, they say, as you increase the number of cores, you don't keep your problem the same, but you actually partition data, for example, and have more threads working on it, and you scale the data set size. Right? You won't increase the number of cores without scaling your data set size. That's what they say. And they say in this condition, Amdahl's law doesn't hold because now you have more data and you have more parallels. Right? That's the gist of it, as I interpret it. Does that make sense? Yes?
Could you restate Amdahl's law just as a refresher?
So sure, yeah. Amdahl's law says basically you have, let's see. As a refresher, you have a program that stays constant. You have, let's say, the execution time of a program is T with one processor. Amdahl's law makes a prediction of the execution time of a program T with P processors, right? Okay? And when you go from one processor to T processors, the program is the same. Data set is the same, right? Program and data set size remain the same. Data set means also input set. So Amdahl's law's prediction is that the speed up of this program as you go from 1 to P processors is this. 1 divided by 1 minus F. This is the non-parallelizable portion of the program, plus F divided by P. That's P processors. Basically, the parallelizable portion of the program can be sped up by P times, and non-parallelizable portion of the program cannot be sped up at all. Right? And this is your speed up. I guess speed up is the same as T1 divided by TP, right? Okay? And there are other assumptions here also. For example, one assumption is that I described in the lectures. Actually, you haven't watched the lecture 1, right? Okay, so that's why. So go and watch lecture 1. You'll see a lot of these. But it's good to ask the question if you don't know it, of course. But basically, one assumption that we cover in lecture module 1 is this assumes that the parallelizable portion of the program is perfectly parallel, right? Now you divide it by P. But that's almost never the case, actually. You don't have perfect parallelism in the parallelizable portion. So that's one assumption. So Gustafsson law doesn't tackle this, as far as I know, that paper. That paper tackles this assumption, which is as you go from one processor to P processors, you don't keep the problem really the same. You keep increasing the data set size. That's what they say. And once you do that, this doesn't hold. And I don't remember the exact formulation. I'll encourage you to read the paper, but maybe you can help me with that. But basically, they say, I don't know if, where's the model. This is a scaled speed up model that they have. Do you remember what these are? Yes. Yes.
My understanding of it is that they sort of attack it from the opposite direction.
Uh-huh.
So they assume that you have some arbitrarily sized problem working on some parallel architecture,
Mm-hmm.
and that it has some amount of execution time which is sequential,
Mm-hmm.
and some execution time that is parallel.
Mm-hmm.
And then they say, what if you were to take that problem and run it on a single processor machine instead?
That's right. You scale the
Now,
size.
instead of having some amount of time s that is sequential and some time t that is parallel, you have s plus n, where n is the number of processors,
Mhm.
times p, which now runs on a single core processor.
Yes.
So
Mhm.
now you have actually a slowdown, but if you just reverse the fraction, you get a new equation for the speed up.
Mm-hmm.
And instead of being the curve, like for Amdahl's law, you get a
Linear curve.
function.
Mm-hmm. That's right. Because you've scaled the size of the problem, right?
Yeah.
Yeah. So, yeah, go ahead. Okay.
It's just an extension of the Amdahl's law.
Yeah. Mhm.
So this is Amdahl's law. I assume that the data size is fixed.
Yeah.
And we can extend that model considering that the data set may be fixed. So I
Mhm.
would say that
Mm.
this is not
Yes.
like Amdahl's law. It's just extended.
That's right. So, yeah. So I think I actually agree with what Samira said. There are applications that can work both ways, right? So I think Amdahl what Gustafsson assumes that is that it's looking at a problem. You have a very parallel application potentially with a large data set, and when you run it on a single core, you would like to scale the size. If your application is not that scalable to begin with, you're back to Amdahl's law, right? So you cannot increase the data set size. If you have fixed problem size, fixed data size, that's what you got to deal with, right? You cannot increase the number of processors and always increase your data set size. So I think both equations or both laws, if you will, are applicable in cases of different applications. If your application is such that you care about this data set size and you want to speed it up, and there's no other way you can increase your data set size, well, you're stuck with Amdahl's law, right? But if your application is scalable, as you increase the number of cores, you can also increase your data set, then sure, the Gustafsson's equations are reasonable. Does that make sense? Yeah. So this is called the weak scaling versus strong scaling. Weak scaling is your application cannot scale. Your data set size cannot scale. Strong scaling is your data set size can scale. Yes?
So my question is, how does he assume that the data is just going to scale? Is that something the user is doing or the computer is accounting for?
Yeah.
Or I'm a little confused by how we just assume that the data would automatically scale.
So yeah, it's something the user is doing potentially, right? It's not. I guess you could think about it doing it automatically too, but user can specify that. So think about let's say a large. So this is actually Gustafsson has worked at national labs, I believe. That's what his background is. So he's used to working on these large scalable scientific applications, like a huge matrix multiply, right? If you're doing a matrix multiply on one processor, maybe you want to do it with a small matrix, right? 1,000 by 1,000 matrix. That's actually too small, but take it for the sake of the example. I think now, and you're doing lots of computation at a time. You have lots of parallelism. If you want to do matrix multiply on 100 processors, now you can scale the problem size, right? You can make the matrix much bigger, right? So if you have that kind of a problem, then you can easily scale the size of your matrix, right? But not all problems are that way. If you're doing transaction processing, for example, getting a request from the web, and you're trying to parallelize that, maybe doing a sale in Amazon for one particular thread, that problem is not scalable necessarily, right? Okay. So I think it really depends on the problem that you're looking at, what application characteristics you're looking at. Okay. This is good. You can take a look at this paper also. This is actually a short paper too. But I would argue, actually, one thing I would argue is this kind of application where you can scale the data set size is an easier problem. What Amdahl was more concerned with is taking an application and you cannot do anything to it, but you want to speed it up somehow by exploiting parallelism. That's a harder problem, right? If you can scale the data set size, sure, you can get better linear performance potentially. But if you cannot scale it, now it's a much harder problem. Now, how do you exploit parallelism to scale it? You're back to square one. In that sense, these laws are synergistic. They're not refuting each other, right? Yes?
Yeah, so I just verified my understanding. So it's like when we have better parallel architecture, we can scale our problem so that we can better exploit the parallelism within our problem.
That's right.
Since it is scaling.
Exactly. Yeah, because you have more memory and more processors, you can scale the size of your problem. That's right.
Originally, we had only do some kind of 1,000 by 1,000 matrix multiplication, and do multiple some kind of operation. Just for example, and then later we can do a much bigger size dimension matrix multiplication, but just for several times, so that some bigger multiplication can better exploit the parallelism.
That's right.
From the problem side.
That's right, exactly. Yeah. Yeah. I would actually suggest that you read this paper also so that you can think about it a little bit more. There are other papers that try to adapt Amdahl's law for energy, for example, recently. If you want, you can read that too. But one of the interesting research issues or modeling issues is, how can you make this model a little bit better? This I've discussed a little bit in the lecture too. But I don't believe changing the application is making the model necessarily better. It's just an application assumption, right? Assume that the application remains the same. But how can you model some of these bottlenecks that happen in the parallel portion in Amdahl's law, right? You will see in the lectures, I assume some of you have watched the multi-core lectures, and people have adapted Amdahl's law to take into account heterogeneity, right? Heterogeneous cores. Now this fraction is divided by something else also, because if you have a heterogeneous core, you can speed up the serial part of the program too. So that's one example of how to adapt Amdahl's law to what you have today. But another example is how do you take into account these bottlenecks that happen in the parallel portion? If you watch the lectures, you probably can tell me what those parallel bottlenecks are. Who's willing to? There are three fundamental bottlenecks in the parallel portion of a program, right? That's good. You've got two: synchronization, load balance, imbalance, and resource contention. That's right. Excellent. So collectively, you got it. And actually, if you have a fourth one, I really like to hear, because I think that's really that would be a breakthrough, perhaps. This is the best I could come up with over the years. But yes, those bottlenecks. How do you model that better? Amdahl's law doesn't model any of that, right? It just assumes this parallel portion is scalable. Parallel portion is perfectly parallel. But that's not the case. And some of the papers you've been reading, the papers you're assigned, for example, accelerating critical section execution using asymmetric multi-core architectures, try to accelerate the parallel portion, not the serial part. Okay. So it's exactly what I would like to do in the recitations, basically. This is an example. We wouldn't have talked about Gustafsson's law at all if we didn't really have this decoupling between the lectures and the recitations. Now we can have more time to go in depth into things like this. Okay. Let's see. So I guess we've covered one more potential research topic. How do you actually extend this to the parallel bottlenecks? And maybe different kinds of systems, like accelerator-based systems. That could be interesting too. Actually, one other, I think, interesting research topic is this could be interesting to people who want to do some sort of analysis, modeling of real systems. You can take applications that are currently used a lot. For example, let's say a database, or an in-memory database, or a key value store, or a graph processing application like GraphLab that's developed here, or something else that has some multi-threading employed, and that does have some of these parallel bottlenecks. And you can do a good characterization of where these bottlenecks occur. That would be very interesting, as long as you pick a very important application and you do a rigorous characterization of where does this application spend time synchronizing? How much time is spent that way? What are the locks? What is the reason for contention? Where are the barriers at? That's another reason for parallel bottlenecks, right? And why do threads arrive at the barriers at different times? If you do a very good analysis of this could be a very nice project also, in my opinion. So if you're interested if you're inclined towards a project like that, I'd strongly encourage you to consider things like this. And then, because once you have this understanding, you can say, oh, these locks are contendant, and for this particular reason. Maybe it's because the locks are not implemented nicely in the application, right? That's usually the case, actually. That's almost always the case, and that's why a company like Oracle employs thousands of engineers to over decades to optimize those locks, right? To minimize the contention. But that's not always a good solution, right? You've seen through my lectures that there's this fundamental trade-off between the architects and the software designer or programmer, I would say. And that fundamental trade-off is at play here. You can tell the programmer to optimize their locks, and they will bang their heads on the wall and try to optimize those locks for decades. And they will do it after a lot of pain, right? And while they try to optimize locks, they will have issues in terms of multi-thread programming. So if you're using Windows, Windows hangs a lot of the time because of a lot of those multi-threaded programming issues, actually. There are a lot of shared resources between different programs like Excel, PowerPoint. At least it used to hang. I don't use Windows anymore, but it used to hang because of those bugs. And the problem, you can blame the programmer saying that why didn't you program it correctly? But it's a difficult task. It's not easy to program in a multi-threaded manner and get good performance as well as correctness. And if you want to maximize your performance, you start reducing your critical sections, and that becomes even harder for the programmer. So it's good to look at solutions that make life easier for the programmer And those solutions usually add additional complexity to the life of the hardware designer, architect themselves. Right? And you've seen this with accelerated critical sections, for example. Now the architect needs to accelerate the critical sections underneath, right? And we've seen this many times in 447, and you've looked at the background material. Virtual memory is one good example, right? It's great for the programmer, but maybe not so great for the architect, although we design it today, right? Yes?
So one of these bottlenecks is obviously come about with shared memory. So what's your opinion on like the new developmental OSs that are built with like message passing, like barrelfish and factored operating system?
Mm-hmm.
And do you think those kind of like the message passing kind of systems will replace shared memory as we build like bigger multi-core machines?
Mm-hmm. So that's an excellent question. This is actually a very old debate in computer architecture. Okay, the question is we've been talking about shared memory, but there are alternative systems that you can design that can use message passing, right? And there are recent developments in the operating system community, like barrelfish, which is like a message passing operating system, and FOS, factored operating system, which is a similar thing, at least at the high level. Do we go back to message passing instead of using shared memory? And this is a very old debate, I think, in computer architecture and systems. Do you have a shared memory model exposed to the programmer, or do you have message passing? And we covered this in the in which module is that? Let me just check. So this is your website. Yeah, programming models and architectures. I don't know if you watched that one, but yeah, I'd encourage you to watch that one. It's not due yet, but so we'll get to that. But to answer your question, and this could be another interesting project topic actually. There are advantages and disadvantages to both. And then there's also the question, what does the programmer see and what does the hardware employ? Right? Because you can actually decouple these things. You can have, as you will listen to in my lecture, you can have shared memory model exposed to the programmer, but underlying the hardware can be totally message passing. It may not have any shared memory. And it could be vice versa. Message passing model exposed to the programmer, you can have shared memory hardware underneath. And I have a slide in that lecture that talks about different options and upsides and downsides, because you can have a layer, abstraction layer, right, in between that basically translates shared memory operations to message passing operations. Which means that all of the models are actually at the very low level end of things. If you think of a load, it's really a message, right? You can think of that as a message. You're doing a load and you're sending a message to some place, to the memory controller, and the memory controller is giving you back some data. So it's really a send and receive. So that abstraction enables basically different models. So in terms of scalability, message passing can scale more, in my opinion, too. But the downside, one of the downsides with shared memory is keeping it coherent becomes difficult. I guess there are two things. Everybody needs to see the same address space in a scalable multiprocessor. And also, you will very likely need to keep it coherent. And you will employ caching, things like caching, and you will likely need to keep that coherent. Those are the burdens, if you will. The upside of the shared memory, and this is debatable again depending on the application, it's usually easier to program and reason about when you're writing the program. Because you don't need to deal with whether you send a request to some other thread and receive a request from some other thread, right? Receive some data from some other thread. You say, this is the memory location. I'm going to update it. And everybody else can update it. So you have a shared counter, for example. For example, I had this example of different threads processing different parts of a book and trying to generate histograms of the letters, right? It's a lot easier if you have a single histogram, single global histogram, and you have a bucket for A. And that's a shared memory location, right? Basically, every thread can say, oh, this is the number of A's I've seen in the pages that are assigned to me. I'm just going to increment that shared memory location. As long as you can synchronize those increments, it's great. So that's an easier programming model for many applications. That's the upside of shared memory. And that's the downside of message passing. So the other downside of share, so this comes with a downside also. Now the threads can actually destroy their data, right, if you don't synchronize them properly. Whereas message passing kind of forces programmers to think about synchronization explicitly. In that sense, it's a difficult programming model also, because now you need to think about send and receive. So if you forget a send and receive, well, too bad. Right? You'll get a wrong program that way. But with shared memory, it's more prone to errors, because now any processor can write to any other's address space, right? Because the address space is global. That's the downside. So let's go back to scalability a little bit. I think in general, message passing can be more scalable, because you don't need to keep things coherent, and you don't need to find a memory location across this huge address space. So I think going forward, and I don't think the answer is given yet, because previously in the 1980s and 1990s, the same debates appeared in computer architecture. Should we do shared memory? Should we do message passing? And people converged on shared memory more or less at that time, because it was mainly because it was easier to program. But as we scale systems further, coherence becomes a problem. And address searching becomes a problem. Keeping TLBs coherent becomes a problem, because once you change a mapping in one processor, you need to ensure that that mapping also is the mapping that's used by another processor is not stale, right? You all know about virtual memory. That's the assumption here. How many of you know about virtual memory mechanisms? Okay, that's good. If you would like to brush up your memory, you can watch the 447 lectures. But basically, now you need to keep TLBs coherent somehow also. So that makes shared memory more difficult, I think, going forward. But you don't want to get rid of the benefits of shared memory, because that's easier for the programmer in general. And there are some applications that are much more easily written that way. Yes?
Just briefly, how does message passing compare to shared memory in terms of like extra hardware? Like, where do the messages go from one process to another? Like, A sends B like 3 messages. Do they queue up in some type of memory, or like that belongs to that core? Or?
Oh, so if you want to, you can do that if you have support for shared memory. But you can handle message passing totally in software. You don't need to add any extra hardware. So if you watch this, I don't know if you watched this yet, but if you watch this, we'll talk about the convergence of architectures, which says that the hardware can be the same for both message passing and shared memory. Maybe you don't, actually, even for shared memory, you don't need coherence. You'll see that. What if you have message passing? Basically, you don't have coherence and implement shared memory on top of it. It's tough. It's not easy, because now you need to ensure coherence at the software level, right? You can lock a page when you're updating the page, and you can unlock that page afterwards. But basically, the shared memory, the message passing hardware doesn't need any extra support. You can do it purely in software.
Would you like run into the same TLB errors then?
So you won't, because same TLB errors. You won't, because the address space of this processor will be totally different from the address space of this processor.
You just invalidate everything.
That's this processor cannot do anything to the address space of this processor, right? When this processor wants to communicate with this one, basically it will send a message saying, here's a function I would like to execute. Maybe it will know the function name somehow. This is very much similar to distributed systems programming, right? If you've done programming with remote procedure calls, that's essentially message passing, right? What you're doing is, or server-client programming, client-server programming. The client is telling the server, please execute this function for me. And it knows the function name or some handle of the function. It sends the data. And here's the data packets. Take them, and there's some special area in memory that the server stores those. And then the server handles them transparently to the client, right? The client has no knowledge of what memory locations those data packets that are marshaled to the server are stored. So there's no single address space. So the TLB problem goes away. Coherence problem goes away too, because well, you don't now you don't have the same copy of the data because the address space is not the same, right? Yes.
This is a similar debate compared to loosely versus tightly parallel architecture.
That's right, yes. So basically, tightly coupled multiprocessors have a shared global memory address space, which are their shared memory hardware. Loosely coupled multiprocessors don't have that shared memory, shared global address space, which means that they're usually programmed by message passing. So that's the hardware level. Okay. So one interesting question going forward, I think, these are also potential research project topics, is how do we scale coherence as we add more cores in a shared memory hardware, shared memory processing model? This could be something you can think about. And there's been some recent works that I mentioned in one of the lectures, and I believe that was the coherence lectures. Yeah, cache coherence lecture here. That try to look at scaling coherence to hundreds of nodes. And this becomes an important problem because if you're actually operating on data that's private, that nobody else needs to know about, even today, in today's systems, even those cause overheads. Because what happens is you need to ensure that nobody else has that data, right? So I'd encourage you to look at the cache coherence lecture. I know we haven't been there, but some of you have taken 447, and we've covered cache coherence. The second thing is, how do you get the best of multiple models? So can you design hardware that can partially do a shared memory and partially do a shared message passing? I think that's an interesting direction going forward. Also, this leads to some different execution models. And if you look at the asymmetry lecture, there's one example of that. We talk about data marshalling over there. So in the asymmetry lecture, one of the ideas is when you're operating on shared data, when you have a critical section, ship that critical section to a core that's dedicated to execute those critical sections. So this is a model where all of the shared data, in the ideal sense, all of the shared data is operated on a single place. In a sense, you're sending messages, right, to the shared data. Shared data stays in one core's cache, and you send messages to it saying, execute this set of operations on this shared data. That's what a critical section is, right? It's operating on shared data. So if you keep all of your shared data in one place and send your critical sections to that shared data, now that's very much similar to message passing, right? You're really passing messages to that server that's handling all the critical section requests from all these different clients. Now the problem is sometimes shared data is needed in other places also, but anyway, you can look into that. So that's one example of message passing. So incorporating some of these mechanisms, that are message passing like mechanisms, into the shared memory model is very interesting, I think. But that doesn't change the programming model. The programming model is still shared memory, right? The hardware is still shared memory. But you incorporate some message passing mechanisms to improve performance. Data marshalling is another example of this. Basically, you can think of data marshalling as you not only send the critical section to the large core, but also all of the private data that it needs. Do you guys know what I'm talking about when I say data marshalling? Okay, some of you do. How many of you don't? Okay, excellent. So data marshalling. So I'm giving you the idea of accelerating critical sections, right? Basically, you ship the critical section to a large core, and assume that all of the shared data stays on the large core. Now, shared data is good, nice, but when you write a critical section, sometimes you need inputs that are generated by the thread that's executed far away, right? Let me erase this and try to show this way. So let's say you have a bunch of small cores and a big, large, fat core that actually has a large cache, and assume that all shared data is here. And one large core gets to a critical section, and it sends a request to the large core. Large core is a queue of critical sections. We call it the critical section request buffer. And sends this core sends a request to this large core saying, large core, please execute this critical section. Now this critical section accesses some shared data, but it also needs some private data. Right? For example, in the histogram example, the critical section can be add to global histogram. Right? Remember, each thread is computing the histogram of letters in the particular set of pages that is assigned to it in a book, for example. The thread computes a local histogram. Maybe there's a function called compute local histogram, which puts the data into a local variable, local histogram, right? Now, you need to take that local histogram and add it to the global histogram, which is what this does. And this needs to be a critical section because the global histogram is really shared by different threads, right? And that stays in this course cache. But now you need to send the local histogram somehow. This is called the private data, thread private data. It's visible only to this thread, but it needs to be merged with this shared data, which means that if you're shipping the critical section to the large core, you'd better ship this one also. And this is now, how do you do that? Well, if you have shared memory, purely shared memory here, this large core, when it needs a local histogram in this code, it basically pulls the elements through the coherence mechanism, right? But you can still accelerate that, even if you have shared memory. And that's what data marshalling does. The idea of data marshalling is somehow to identify this data that's needed by the critical section and send it proactively to the large core. And you'll see the mechanisms when you watch the lecture. But that's the high-level idea. How do you do that? Well, what is done once you do that? Basically, while you're sending, or before you're sending the critical section, you also send the local histogram. Okay? Now we do this on top of a shared memory model, but you don't, if you actually get rid of the coherence mechanism, now it looks like message passing, right? What you're doing is really this client is sending a function to be executed here. Actually, it's a function pointer if it's a shared memory mechanism. It doesn't have to be that pointer. It could be a function by itself. That function is being sent to the large core, and the data that's associated with this is also marshaled to the large core. So it's very much similar to distributed systems programming now, which is message passing based. And you're doing it on chip. Okay? So it's good to think mechanisms like this, I think. How do you actually do this in more scalable fashion? Yes?
There was some processor that had no coherence, right? But cell processor or something.
That's right, yes.
Not become that popular because of the difficulty to use it, to program it.
Exactly, yes. I think I covered that in one of my lectures too. But yes, maybe the ones you haven't watched yet. But yes, cell processors, IBM cell processor, which had 8 synergistic processing elements and 1 primary processing element, which was a control processor. There were no coherent caches in that processor, which meant that the programmer needed to use mechanisms like this. Well, not exactly like this, but programmer needed to actually ensure that coherence is satisfied in the software level, at the programmer level. And that was difficult to program because of that reason. It was difficult to write compilers for too.
So may there be another attempt to try and push that again?
To try eliminating coherence totally?
Yeah.
So that's a good question. If you want to eliminate coherence totally, you need to do it in a way that doesn't punt everything to the programmer. So if the programmer has to worry about the coherence of data, it becomes difficult. But I think if you have a mechanism, and this is where the research comes in, that enables coherence somehow in some other way, or exploits the characteristic of the applications to help the programmer, then it becomes interesting. Okay? So I'd encourage you to watch these lectures and think about these issues. Yes? Oh.
Say, which I think you just said, if you want to try that again, the way to try to do it is to do it all on hardware so that the programmer would not have to deal with that, and you wouldn't have to change the way you program.
That's right, yes. Yeah. That's a tough trade-off also. But it's good to, I think it's good to somehow clear your mind and design with a blank sheet. How would I design this system all over, given the requirements of today? And if you want to do a high impact project, I would encourage you to do that. Sometimes it's tough. But some of these mechanisms, I think, are getting there. Now, there are other people that have proposed basically eliminating coherence totally. And for example, when you get when you execute an instruction from here, and it's accessing some data, you don't pull the data in, but you basically somehow figure out where the data is. This you need to be able to do, and ship that instruction to the data. Right? This is at a very fine grain, right? At the instruction level. So if you design a mechanism like that, you can eliminate coherence totally. Right? I think that's a tough thing to do. If you're interested in this, this is called the execution migration engine. It's from MIT. Their goal is to get rid of coherence. And whenever an instruction accesses a data, you ship that instruction to the data. Right? Now, there are difficulties with it. Yeah?
What is the difference between that and having, say, a 9-way simultaneous system?
9-way.
Or, well, you have 9 cores drawn.
Oh, OK. I see. I see. What's the difference between this? So if you have simultaneous multi-threading, the assumption is that all of those threads share the cache, right? Right. So you don't need to send anything anywhere. Meaning that coherence is not a problem between those threads. So I think what you're getting at is if you have a system where you have a very highly multi-threaded core, you don't need coherence, right? And that's true. The problem is it's very hard to scale that to thousands of cores. So even though I drew 9 cores here, we'd like to design machines that have thousands of cores, right? And it's very hard to design a multi-threaded engine that has thousands of threads. OK? Here you ship every instruction to the data. Now this has a lot of communication overhead, I think. This is a good initial start, good goals. But maybe you can think about how to make it more practical. And I think the granularity of shipping is very interesting. Right? Do you ship every instruction to the data, to its destination? Right? I feel that's more of an overkill. Right? It's hard to justify the cost of shipping an instruction. Because that instruction, now, that becomes tough. But at a coarser granularity, if you find a coarse granularity like critical sections or maybe something else, now you amortize the cost of shipping the instructions to the data. OK. I had something else in mind, some other project idea, but it escaped me while we were discussing. Oh, multi-threaded. Yeah, multi-threading. I think designing very scalable multi-threaded engine is another potential project area. You mentioned 9-way multi-threaded. Even 9-way is difficult to do today, actually, because they share the pipeline in a very fine grain, right, concurrently. And you get cache thrashing if you actually have 9 threads sharing an L1 cache or even an L2 cache. Can you design architectures that can support or that can give the illusion that you have many threads while having few hardware contexts? I think that's an interesting research direction. And we've discussed this yesterday. And I've discussed with several of you some of potential research directions, so feel free to stop by during office hours or talk with TAs also. It's good that you're discussing these directions. But that's another good area to look into. How can you have, let's say, 4 hardware contexts, but seamlessly make it look like you actually have 1,000 hardware contexts? It's like virtual hardware contexts, right? Now, it's done today, right? This is multi-threading today, but that's a lot of overhead. So you have, for example, 4 hardware contexts in one of the processors. Actually, Sun Niagara, for example, has 4 hardware contexts, right, in a single processor. I cannot keep up with all of these new processors, but they have some hardware context, some hardware-based multi-threading. The fundamentals are the same, right? The numbers change. But today what's done is when a thread stalls, you can execute from the other threads. You can switch in you can execute from the other threads for which you have a hardware context. But assume that all of the threads have stalled. Well, too bad, right? If they've stalled for a cache miss, 500 cycles, you don't have any mechanism to switch in some other thread. Well, the only mechanism you have today is basically going through the operating system and saying, deschedule some of these threads and give me new threads. But that's a lot of overhead. That's a lot of context switch overhead because you're involving the software. But can you have some hardware support to actually do this context switching relatively easily without a lot of performance overhead, without going to the operating system? So that's that kind of project could be very interesting also. I'd encourage you to think about it. Basically, how do you more efficiently utilize the 4 hardware contexts you have with potentially some mechanisms that prefetch the hardware context into the hardware, into those? OK. What else? This is good. We're having a lot of discussion. I don't think I have any other slides to cover. Any other questions? Shall we keep going? Anything else you would like me to go over related to the course? Yes?
So is it required to have teams of 2 for the project, or is that just encouraged?
So that's, I'm in general very flexible, but I would strongly encourage teams of 2. In some cases, I can make exceptions for teams of 1. I'd rather not do that because that's going to be a lot of overhead. In some cases, it could be 3. But you'll have to definitely talk with me. So there is definitely flexibility, especially for online students who are listening to this. Actually, let me handle that for the remote students also. It's a more difficult problem for them, right? Let's see who else is there. We have 7 of you here. But for the remote students, the projects, one idea is to do geo-distributed projects, which is actually nice, which is enabled by this online course, right? So I encourage you to, I sent you an email yesterday. I'd encourage you to talk with each other and try to find topics that you can work on. But I'm open to single-person projects too, especially for remote students, because I realize the downsides of communication, right? Communication overhead, which we will cover also. That's basically the synchronization overhead, right? So actually, yeah, remote students will have that synchronization overhead. You will have that synchronization overhead much easier if you actually team up with someone over here. So all of the parallel processing overheads apply to the team project too, right? You're really doing parallel processing in a team project. You have synchronization overhead, the cost of which is lower if you're local, and the cost of which is much higher if you're doing this remotely. You have the load imbalance overhead, which I will talk about a little bit. That load imbalance is important because you would like to balance the load between the partners. And the best relationship is that way, right? You really want to balance the load. So don't rely on one partner to do the project. That just doesn't work. As I said, at the end of the class, I'll ask each of you in a group to evaluate how much other partner contributed. So for a 2-person team, I'd prefer that to be 50%. Of course, there are sometimes one partner pulls and another partner has something to do, but sometimes the other way around. But on average, the feeling should be 50%, right? Yes?
Just out of curiosity, what happens if one partner reports that they did 90% of the work and the other partner reports that they did 90% of the work?
Oh, wow. then we'll talk with the partners. Yeah. So it won't be like I take whatever you say. We'll have a conversation then. I hope that won't happen. But yeah. If it's in the ballpark, that's fine, right? OK. So that's the load imbalance. I guess there's resource contention also. I'll let you figure that out. Don't work on a single computer. together. Not always, at least. But sometimes it's good, actually. Pair programming is a great way of finding bugs, writing better software, and actually learning in many different ways. Do you guys know pair programming? Yeah, at least many of you. Pair programming is basically a practice where you don't program by yourself, but you program together. And sometimes you even sit together. Actually, I like sitting together. So if you do that, you can be more productive. This is similar to the idea of slipstreaming. Do you know the idea of slipstreaming? Yeah, we covered this in, actually, let's see. Oh no, it's not there. 2.5. It's going to be covered in 2.5, which is speculation. The basic idea is, I'll just give you the basic idea. And the good ideas are usually, you know the basic idea, the rest is how to implement it, right? The basic idea is you have two cores. They both execute the same program, except one core executes it speculatively and omits some instructions, and it gets ahead as a result of that. And the second core is redundant. It executes the program fully, but it uses results like cache misses generated by the earlier core, or results, early computations that are done by the earlier core. The first core executes some part of the instruction stream and generates the results, predicts the branches early, hopefully. The second core uses that information. So the second core speeds up, right? Because the first core gets to these cache misses much earlier and generates those results. And the first core also speeds up because it can actually synchronize earlier with the previous core, right? The previous core gets to some of these cache misses earlier, and the first core can benefit from that. So now both cores can run faster to execute a single program. That's the idea of slipstreaming at the high level. And there have been many different versions of it, which we discussed in that lecture, dual core execution. How do you get ahead is an interesting part. But basically, pair programming is kind of similar, right? As one core, or one of you, can execute and do something on the screen, and the other core can help you. The other person, your partner, can help you. I like applying these different concepts in computing to real life. I don't know if this is a perfect analogy, but it's kind of similar. Actually, slipstreaming the inspiration for the name, as it's described in the paper, it comes from Formula 1 races or NASCAR races. Basically, if you're racing, if you're doing car racing at very high speeds, like 190 miles per hour or higher, if another car comes close to you, this car reduces the drag of the car in the front. So now the front car can go faster a little bit, and the back car can go a little bit faster. So they can both increase their speed by 10 miles per hour or so. And that's why you see all of these cars gathering together if you watch a NASCAR race, because they want to increase their speed by reducing the drag. If you're alone, you have a lot of drag that's affected by the airflow. But if someone else comes next to you, that reduces that air drag. It's fun. Maybe you can develop some other techniques that you can apply to computer architecture in this course, like that. If you're excited about some other area. OK. Anything else that we should cover today? We don't need, oh, by the way, in these recitations, we don't need to go all the way for 2 hours. I'll just end whenever you get tired. And we can certainly schedule another recitation. I guess, do you guys want to have a recitation on Friday? Yes?
Will it be better to have a poll between the 3 days to see which one would work the best for everyone?
OK, actually, that's a good idea. Can we construct that poll? Yeah. Let's do that poll then. I guess I assume you're here because this works for you. No? You're here because, oh, you came late. That's right. I guess let's have a poll here first. What day works better? Who says Monday? Monday, 7:30 to 9:30. Some people say that. Not everybody, though. Who says this time? It's great. Okay. Who says the Friday time is good? I don't remember the exact time, but. Oh, okay.
In the morning or the afternoon on Friday?
In the morning. So what will happen with the afternoon is afternoon part will be actually dedicated to CS lectures. So it will be a lecture session. You're certainly more than welcome to attend that, but if you watch my lectures, it'll be repetition. But it'll be the morning session then, right? Is it 10:30? Yeah. So Friday, 10:30.
I think Wednesday is going to be hard for TAs to attend.
Okay, that's right. But Wednesday it looks like there are a lot of people. Okay, so I think we'll have an online poll, and maybe we'll have a write-in. No, maybe we'll have a doodle also, because I'm happy to be flexible also since it's an online course. Are you guys? Do you think you'll be available at other times potentially? Tuesday and Thursdays? Is that usually better, Tuesdays and Thursdays? Who says yes for Tuesdays? Oh, it depends on the time. Evenings? No? Mornings? Tuesday mornings? Maybe. I guess we will have the polls, but yes, you have a question?
Even if it's only, I still need a time.
Okay, yes. So what we will do, I think, is maybe we should do a broader, we should do 2 polls. Which discussion time you would prefer? And also we should do another poll saying, I guess let's give out potential dates that I'm available at and perhaps the TAs are available at, and ask which times are better. So this is another flexibility that the online nature of the course allows us. I think we'll do that. So please respond to the polls. Everybody who is listening also, and everybody who's not here also, please respond. Then we'll find the time that works for everyone. Well, that's going to be tough, but we'll find a time that works for most people. Okay, so I think for now let's plan on doing the recitation on Friday, because I'd like to discuss some more project ideas. And it'd be great if you can do well, you'll have to do the readings because the readings are due Friday. But watch the lectures, all the lectures that you're assigned until Friday, which is parallel processing basics, parallel processing task assignment, multi-core processors, why, and their evolution and design. Do the readings associated with them, and come with some questions. And then we'll hopefully discuss your questions as well as talk about some project topics. At some point this week, we'll post a project topic handout that includes some of the project topics that I described today, but some of them are not included. Hopefully you'll start studying that, because your project proposal will come quite soon. That's why I would like to focus some of the recitations, early recitations on project topics. Okay? I guess any questions, any other questions before we part? Yes?
Are all the assignments going to be paper reviews or kind of?
So we'll adjust as we go along, but most of the assignments you will do will be paper reviews. We're not going to have any homeworks in this course, but there may be some exercises, small exercises to prepare you for the exam, potentially. Okay? And we'll definitely communicate over recitations as well as through the learning environment. Okay? Okay. No questions online either? Okay. Okay, I guess I'll see you Friday then. Come with good questions.